So we left off on slide. No, we left on slide like whatever this is, 27. Yeah, I'll recap. Let me recap this again because I know a lot happens here. The way muscles work, how they contract. You have a neuron. It's called a motor neuron because it controls muscles and controls movement. You have a motor neuron. That neuron gets activated, and that's a whole other chapter. Neuron gets activated, sends a signal down its axon, and we reach the axon terminal. At the axon terminal, we've got vesicles full of neurotransmitter. Neurotransmitter is released into the synapse, and it binds to receptors on the motor end plate. This whole region here, axon terminal, synaptic cleft, motor end plate, this whole region is called the neuromuscular junction. These receptors, again, are found on the motor end plate of the sarcolemma. The sarcolemma is the special plasma membrane of muscle fibers. When this receptor gets activated, what gets activated next? A membrane receptor gets activated, and then what other membrane protein also gets activated? What opens up? What membrane protein opens up? We've only talked about a handful of membrane proteins. Receptors are one of them. What else can membrane proteins do? What? It's related to sodium. So, what about iron? How does it? What about ions? What about it? What about sodium? What do we want happening in this muscle fiber? Like neurotransmitter binds to this receptor, and then what?
And then it goes down the T2.
Not there yet. Oh, that's the next step. You're on the right track, but I need the thing. What is the thing that this activates? A transport protein or a channel. You need to say it. I need to hear it. Yeah, bad ears. Okay. A channel opens up which lets sodium in. Sodium rushes in. That's what electrical current is. Sodium rushes in. The T tubules help that electricity spread deeper into the fiber. That electricity spreads, and we then activate the sarcoplasmic reticulum. For how that happens, you'll get to that in physiology. Sarcoplasmic reticulum is activated. Open up calcium channels, calcium transport proteins. Calcium rushes out into the sarcoplasm. Calcium binds to which molecule next? Troponin. Calcium binds to troponin. Troponin moves which molecule? Tropomyosin. And now that tropomyosin is out of the way, what can happen? Which two molecules can interact? Myosin can bind to actin. And that's the power stroke. Myosin grabbing and pulling an actin. Here are the thick filaments of myosin. Here are the thin filaments, mostly made of actin. These myosin heads grab and pull on either side. So on this side, they're grabbing and pulling. On this side, they're grabbing and pulling. So the sarcomere shortens. That's what contraction is, Nora. Is this what happens? In rigor mortis, what's happening is that it already stays contracted, but it doesn't relax. If you want, what takes energy is relaxation. Relaxation and, what's the word? Just getting ready for the next contraction. Like my example is, say you've got a mouse trap. If you want to set the mouse trap, it takes you energy to pull that back and set it. To snap it takes no energy. So like you can stay contracted, but to reset it will take energy. When you're dead, you got no energy. Which is why animals get stiff when they die. Okay, again, a motor unit, you've got one neuron activating many fibers. In areas with precise control, you don't want a lot of divergence, just controlling 2 to 3 fibers, but it can be a lot, thousands. Like if you want to control your quadriceps, that's one neuron controlling thousands of fibers. So you're recruiting it all at once. Whatever it is, the idea is that you've got a neuron here in the spinal cord or somewhere else. Its axons branch and then form several neuromuscular junctions. At any given time, we're not just limp. Even when we're asleep, even when we try to relax as much as we can, our muscles have a slight contraction. The term for that is muscle tone. If you've got rock hard abs, you've got a lot of muscle tone. But everyone's at least got some tone, unless you're just a lifeless body. But we're not. Everyone's got some. We're not just blobs. We need tone because otherwise, yeah, we would just be blobs. We need to have some kind of posture. We need to have some kind of support. So our muscles are always slightly contracted. That's what muscle tone is. Muscles are always slightly contracted. For an even more complicated process that we're not going to get into, but you probably will in physiology, how do we know how to keep our muscles toned? Our muscles have to, how do I put this? In order to know how much to stay contracted at a baseline, how much contraction that our muscles should have at a baseline, we need to know how stretched out our muscles are. To know how stretched out our muscles are, we need a receptor. So just like we can sense when we're touched or sense pain or whatever, we can sense how stretched out our muscles are. The receptor that detects the level of stretch of our muscles, that's a muscle spindle. We're going to see this in more depth later, but just so you get an idea of what it looks like. Let's say we've got muscle fibers here. Here's a muscle fiber. Here's a muscle fiber. Surrounding or in between all this muscle fiber, you'll find occasionally a muscle spindle. Muscle spindles are special receptor cells. They're wrapped in a connective tissue. That's what's shown here. Here you can see connective tissue, and the muscle spindle is inside. This detects stretch, and it tells your body how stretched out the muscle is, and that then tells your body, okay, contract your muscle this much. Again, it's a pretty complicated thing. You'll learn more about it in physiology, but I at least want you to know that throughout your muscles, you've got muscle spindles. You recognize them by looking for a connective tissue capsule that surrounds them. Okay, so how do we actually gain or lose muscle? What does that mean? Usually when you gain tissue, you have mitosis happen. Like when we gain skin, when we have to have new skin, we always are producing more and more cells. With muscles, it's not that we're gaining cells, it's where the cell sizes are gaining in size. Kind of like with fat. When we went over adipose, usually the adipose cells, adipocytes didn't undergo mitosis, they just grew a lot, like grew fourfold. These, when we work out, when we do activities to increase muscle mass, the term for that is hypertrophy, literally elevated growth, hypertrophy. Troph means growth. Cells are getting bigger. Muscle fibers are getting bigger. The basic process of what happens is that muscle fibers get slightly damaged when we work them out. Muscles get slightly damaged when we work them out. So we need cells to heal them. And when they get healed, they add more stuff. You get more myofibrils. You get more organelles. Your cells grow and get bigger. Muscle spindles are more active, meaning you get more toned. So people with really good musculature, they feel very hard because the muscles are contracted even more. The opposite of hypertrophy is atrophy. This A means without growth, atrophy. I don't know how you can see this, but what's shown here is a bunch of muscle fibers in cross section, and they're really close together. So here's a muscle fiber, here's one. It's all smushed together. If your muscles are atrophied at a tissue level, you can start to see even more gaps between them because the muscle fibers are shrinking in size. This happens when you don't use them as much. You're not causing any growth in them. They decrease in muscle mass, you decrease in muscle tone. The term for not the opposite of toned is flaccid. Flaccid means like limp.
How long does it take for atrophy to set in?
How long does it take for atrophy to set in? That's a good question. It could take a week or two for like it's a gradual process. Atrophy is a gradual process. For it to be permanent atrophy, roughly 9 months. Like say you're bedridden and you can't move, 9 months for like damaging atrophy, where you can't come back from it.
Like 6 months, you can't do anything because you're bedridden. You lose some muscle mass. It shouldn't really be permanent.
Right. Say you're bedridden for 6 months and you lose muscle mass, which you definitely will. Will it be permanent? Not necessarily. Which is why, say you're bedridden, it's best that you, if you can, move at least a little bit, or even stimulate your muscles with like those electrical stimulator things. You want to get some movement going for circulation reasons, for muscle mass reasons. Yeah. But as far as like the course of how quickly it happens, I'm not quite sure. But it's a gradual thing. You've probably heard of the difference between slow twitch and fast twitch muscle. So what does that actually mean? Slow twitch, the term twitch, that's referring to how quickly can you contract a muscle. So slow twitch means you contract it slowly. If you contract it slowly, that means these muscles are better for endurance. They're not the best for strength, for power, but they're great for lasting a long time. So slow twitch fibers are adapted for high stamina, low tension. So they can last a long time. They're not generating a lot of force. Things like posture or walking. You've all heard of hemoglobin? Where do you find hemoglobin? In blood cells, in red blood cells, erythrocytes. Hemoglobin, its purpose is to carry oxygen. There's something called myoglobin, which its purpose also is to carry oxygen. But it's not floating around in the bloodstream. These are within muscle fibers. So basically, you've got blood flowing in between these muscle fibers. They transfer oxygen. Myoglobin will take even more oxygen, acting as a reserve. Think of this as like it's hogging more oxygen than other cells, which is good. You want oxygen for these muscles. Myoglobin makes, or think about hemoglobin. Hemoglobin makes red blood cells dark red. Myoglobin makes these cells darker. Slow twitch fibers appear darker because of the myoglobin. So here's an electron micrograph of, if you have to guess, is this top one slow twitch or is this bottom one slow twitch? Yeah, this is slow twitch. This is our fast twitch, which we'll mention in a second. It's darker because of the myoglobin. So this is a longitudinal section. Here's a cross section. You can see the slow twitch is darker than the fast twitch.
It's just because it doesn't have more oxygen?
The fast twitch has less oxygen. It does not have myoglobin.
Is that slide for that picture from the same muscle?
Is it from these two? Oh, I see. Is this from the same muscle? That's a great question. I would guess so. It'd be weird for it to be like connected but not be in the same. So you can have a mix of different fiber types in the same muscle. You have a mix of different fiber types in the same muscles.
So would your core muscles be like slow twitch?
Would your core muscles be slow twitch? Mostly yes, because we're mostly using our core for posture. You can train and improve them to become more fast twitch.
Yeah, so is there, like in terms of training, like the slow twitch and fast twitch or fast twitch and slow twitch, you can do that? Or is it just like where you got it?
Yeah, can you train muscles to be a different type of muscle type to an extent? There are limitations genetically as far as we know.
And then are like all bodies kind of like 50-50? Do they have like the same relative spread, or is it like one person can be 90% fast twitch?
Is it the same relative spread? I'd say it's more about where the location of the muscle. Like muscles for walking, muscles for posture, you need slow twitch because you need to just maintain your posture. You need to walk around all the time. That's stuff you can do for hours and hours. So it's more about the muscle, and then from there it's genetics and what you do on a daily basis. Besides having lots of myoglobin, which makes them darker, they have lots of mitochondria, and because they need lots of oxygen, you need lots of blood supply. So you can see all of these gaps in between. These are for blood vessels to deliver more blood to these muscles. More blood is delivered to these muscles. That's slow twitch. There is an intermediate twitch. I'm not going to go over it. We're just going to go over the extremes. Slow twitch type 1, fast twitch type 2. I said the word twitch is about how fast it's contracting. These contract fast twitch. So they're great for creating high tension, short bursts. They're not good for working for a long time. Like a simple comparison would be marathon running. That's obviously you're gonna need slow twitch. You're gonna need that for a long time. Versus sprinting, you need really good fast twitch for that. And you can't sprint at that speed for extended periods of time. You can only do it for a short amount of time, and then you're winded. The opposite is true here. They don't have as much blood vessels, low vascularization. So that means that they look paler, which also means they get tired faster. But they are stronger. And one way that we can see that they're likely stronger is that the diameter, here's cross-section, the diameter is wider, it's bigger. Larger diameter because they're packed with myofibrils. Our eye muscles are fast twitch, which is why it can get tiring if you're staring or looking at something for a long time. Powerlifters, sprinting, you need a higher concentration of fast fibers. And you can increase the proportion of fast fibers, again, to an extent. Yes?
So you talked about eye muscles. It says it gets tired like staring.
Staring is one thing, or even just like if you're tracking something.
So what happens when you get too tired? We blink.
Oh, what happens when you get tired? You blink, or you just need to rest your eyes. I mean, you'll feel it. You'll feel that achiness. It's like when if you work something out, you just need a minute for it to rest. Same for your eyes. With kickboxing, lots of things. I mean, you'd be using both because I mean, like for basic posture, that's slow twitch, but for like the sharp movements when you're kicking or punching, that's fast. Yes.
Like when you have a migraine, you feel it in your eyes. Is that like your eyes?
When you have a migraine, migraines are due to multiple reasons. It could be nervous, it could be blood pressure, it could be muscular. So I can't give you a good answer for that. It could be a number of reasons. Cool. So slow twitch, lighter in color, smaller diameter. Fast twitch, large in diameter. Wait, what did I say? Slow twitch, darker in color. There we go. Because of the myoglobin. Smaller diameter. It can last a long time. Fast twitch, larger diameter, stronger. They don't last very long, and they're pale. Okay. So hopefully all this makes sense now. You can explain this whole pathway Like it's nothing, right? Why I show you the rowers again? It's like how the myosin heads grab and pull. These are the myosin heads cocking back, and then completing the power stroke. Cocking back, completing the power stroke. That's how contraction happens within a sarcomere. Take a moment, please. Amy. There's two separate ones.
Paralyzed.
I'm sorry?
For what reason? Paralyzed. Like for surgery?
Or to harm an enemy.
The teaching was on
Or Botox. Raise your hand if you need more time. Okay. Hands on 3. 1, 2, 3. Keep your hands up. Cool. Find someone with a different answer. Argue why you're right. Go ahead. What did you think? C. Why? Blocking receptor channels on muscle fibers.
Sound wrong.
I'm asking for your reason. I need a reason. All right, let's start with this. There are 4 things listed there. One of them is not on a muscle fiber. One of them is on a neuron. Which one's on a neuron? Yeah, okay, so we can cross that out. So, okay, we want to find some place where we can find receptors. Do T-tubules have receptors? Do sarcoplasmic reticulum have receptors? Or do motor end plate have receptors? Do you know what those things are? It's not T-tubules? Okay. And what does it do? What's a motor end plate? That must be it. One more time, let's see your hands, please. 1, 2, 3. On 3, say the letter. 1, 2, 3.
D.
Yeah, it's D. D. Motor end plate is here. Axon terminal is here. I can just show you. Here's the axon terminal releasing neurotransmitter to the motor end plate. The motor end plate has those receptors that then activate those transport proteins. T-tubules are for the charge to spread. Sarcoplasmic reticular for the calcium to be released. Axon terminal is on the neuron, not on the muscle. Thank you. Here's another question. Thanks.
How many?
Raise your hand 3 more time. I saw that. Okay. Hands on 3. 1, 2, 3. 3, say the letter. 1, 2, 3. Wait, what? Say it again.
So
The key word here, the key word here is to sense. If you want to sense something, you need a receptor. This is a receptor. This is how the neurons communicate. What are you going to say?
Oh, I was just gonna say, so the spindles are also responsible for like the I don't know, because like the sensation of muscle is like the sensation of like contraction.
The sensation of contraction, is that muscle spindles? I mean, muscle spindles will be activated when you contract because the muscle is getting shorter. But this isn't a conscious thing. When you sense your muscle stretch, this is not a conscious process. This is something that's automatically, unconsciously done.
So like when you like stretch.
When you stretch, you're activating these, but you're also, when you feel a stretch, you're activating other things too. So your conscious sensation, those are like, thank you. The conscious sensation, that's things like proscenium corpuscles or pain receptors. The unconscious processing of the state of your muscles, those are spindles. Why isn't it D? Because neuromuscular junctions are how neurons communicate with muscles. So if you want to control a muscle, if you want to control the knee jerk, that's neuromuscular junctions. If you want to sense it, that's the spindle. Katie? Muscle spindles, are they conscious or unconscious? They're unconscious. You don't consciously process the state of your muscle contraction or the state of your muscle stretch. Like you can feel pressure, you can feel pain, but those are separate receptors. This is the state of your muscle stretch is unconscious. All right. We went over, just like when we went over bones, we went over shapes of bones and how that related to their function, and arrangement of, here we're going over shape of muscles and also arrangement of muscles. So we're talking very generally about different muscle types and how that relates to their function. I'm going to simplify it for you. I'm not going to test you on these 3 terms. I want you to know this term here to start. One way that muscles can be organized is that these fascicles can be in a parallel arrangement. So the way that these terms are describing how the fascicles are arranged. Fascicle arrangement. One way in which fascicles can be arranged is that the fascicles can be parallel to one another. So if you look at your biceps brachii, you can see that they're pretty parallel. Your rectus abdominis, your abdominal muscles, they're parallel. Your muscle that helps you supinate, it's a muscle right here, it's parallel. So whether it's a strap or a fusiform or fan-shaped, what this tells you is that by being parallel, they can be really useful for fast movements or large movements. With your biceps, you're doing this motion, it's just in one direction. It's good for a large movement because you're going over a large angle here. Same with your abdominals, you're flexing your vertebral region, your supinator, just turning real quick. This is more detail about, like, they're not all, I mean, yes, this is straight, but they're parallel. Or what I want to say, like things like your pectoralis major, like the ones for bench press or push up, they're they're still parallel, but they come together at a sharper point at one end. So that's going to have them have a weaker pull, but they can change direction more easily. So again, I'm not going to test you on these 3 different sub arrangements. I at least want you to know in general, parallel muscles where the fascicles are arranged in a parallel fashion, they're great for fast or large movements. Pectoralis major, biceps brachii, rectus abdominis, supinator, muscles like that. This next term is called pennate. P-E-N-N-A-T-E, pennate. The term pennate, what that means, let me go back real quick. You can see here, like for the biceps, you've got your muscles here in the middle, all bundled together. You've got a tendon over here, and you've got a tendon over here. So we've got tendons on either side. Pretty straightforward, right? It's not that way for these pennant muscles. Like for this unipennant muscle, the tendon goes along the side. So it's kind of like here's the tendon, and then the fibers are coming off of it. A bipennate, you've got the tendon running up the middle. Bipennate, you've got the tendon running up the middle, and you've got muscle coming off of it. Multipennate, you've got several branches. You've got a tendon in the middle here, tendon in the middle here, tendon in the middle here, and muscle coming off of it. Once again, I'm not going to test you on the uni, bi, or multipennate, but I do want you to know what pennate means. So the fascicles are arranged at an angle, which means now the fibers are shorter than in, say, parallel muscles. With shorter muscles, there's greater force. I don't know if you've ever gone to the gym with a friend who's shorter than you, shorter arms, and they can bench a lot more than you, even though they're smaller. By being shorter, you can there's less, what's the word? Yeah, but there's another more technical word than that. Torque? Some physics word I'm trying to think of. But yeah, shorter distance, it's easier to push something or to move something. Some physics word. Oh, what are some examples of pennant muscles? Muscles of your forearm, like your extensor digitorum, the one that extends your fingers. That's a pennant muscle. Your rectus femoris, this is the muscle that's on your quadriceps. Your deltoid, your shoulder muscle. That's an example. If they're not parallel or pennate, then your other arrangement type is circular. This is where the fascicles form circles, form concentric rings, or at least give the appearance of it. What I mean by give the appearance of it, like a muscle could make a complete loop, or you've got one muscle that's curved here, another fiber here, another fiber here, another fiber here, so it forms a circle altogether. So if a muscle forms a circular pattern, that means when they contract, you're going to close the circle. So you can close your eyes, you can close your mouth. Those are circular muscles. Orbicularis oris, that's the muscle that goes around your mouth. Orbicularis oculi, that's the muscle that goes around your eye. Your sphincters, your skeletal muscle sphincters, like your external anal sphincter, that's a circular muscle. The external anal sphincter, that's skeletal muscle, but there is also an internal sphincter, that's smooth muscle, because that's controlled unconsciously. But by having a circular muscle, we're regulating the opening and closing of something, whether it's eyes, mouth, anus, things like that. Question? Yes, Lynette.
Can you close your nostrils?
Can you close your nostrils? You can do this. I can only do it on one side. I can't do it on the other side.
No, I was just doing it now.
Can you close your nostrils? I mean, kind of, yeah, but I mean.
You're doing it.
We're going to go over some facial muscles. We're not going to go over all the facial muscles, but there are muscles surrounding the nose. That's a little different, I think.
There's a muscle there.
All right, so those three terms will be important. You can categorize muscles as parallel, pennant, or circular. And we'll be going over those types of muscles coming up. Once again, I will not be testing you on the specific origins and insertions, but I want you to know what this means, and it will be helpful in general to learn where these muscles are located, what they attach to. We learned all those bone features for a reason, like the anterior, superior iliac spine. We learned that for a reason because muscles attach to those things. And that can be very helpful, say, if you're a massage therapist or if you're a physical therapist, to know those points, because let's say you feel pain at that point, then you can figure out, well, maybe there's a problem with this muscle, with this attachment. Muscles need at least 2 attachment points. I say bones here, but it could also attach to skin. It needs 2 attachment points. When you attach to something, you need an anchor and you need the thing that you're attaching to pull. So like if I want to pull that whiteboard towards me, I can latch onto it and then pull it towards me. I'm the anchor, I'm the origin, the original point of attachment that we're pulling towards. The thing that we're attaching to and pulling closer, that's the insertion. So every muscle has an origin and insertion. If you want to move your arm, your biceps is attached to, remember the coracoid process? Here's the coracoid process. That's the origin. If we want to move our antebrachial region, if we want to flex it, we need to attach to this radial tuberosity of the ulna. Or sorry, of the radius, radial tuberosity. So we need an origin and insertion. The insertion is generally more distal, but not all the time. Insertion is generally more distal. If we want to move especially our limbs, if we want to move something in one direction, then we generally want to move it back to the other direction. So usually muscles come in pairs. The term for these pairs are agonists and antagonists. It's all relative, which one's the agonist and which one's the antagonist. So it has to do with the action. What is this action coming up like this? Flexion. This is flexion. This is extension. So let's say we're talking about flexion. The agonist for flexion, that's the biceps brachii. Its antagonist would be the triceps brachii. Agonist, antagonist. But let's say I flip it. Let's say I say relative to extension. To extend, the agonist is triceps. To oppose it, the antagonist would be biceps. So it's all relative to which motion you're talking about. So if we're saying agonist for flexing, that's biceps brachii. Then the antagonist, would be triceps brachii. It's all relative to what we're discussing. Agonists and antagonists, and that's what this is showing here. So most muscles come in pairs. They do opposite things, opposite motions. So remember those movements we discussed last week? You should know them. And you should know what muscles do which movements. We got practice with this already. When you describe how muscles move, how muscles act, we can talk about the region that's moving, but I prefer this way, explaining which joint is moving. So if we want to say the biceps we're flexing the biceps, we're causing flexion at the antebrachial region, or I like to say the point where the flexing is happening. So this would be the humeral joint. So I'm going to favor and discuss things in this latter way.
Okay, so why is it that like some muscles in the pair are bigger than the others? Like the biceps are smaller than triceps.
Yeah, why is it that some smaller than triceps? Oh, because there's 3 heads. Why are some muscles bigger than others? I mean, it could have to do with what's the word? It just depends. Like how much load is that muscle taking? Like in back here, triceps, this is really the only muscle in this region for extension. Here we've got the biceps brachii, we've got the brachialis, we've got the coracobrachialis. There's a lot of muscles here. So yeah.
It's like the biceps are the prime movers, and then the triceps are the antagonists for like flexion. But on the legs, it's like the opposite. The quads would be the prime movers, and then the hamstrings would be the.
Well, it just depends what you're discussing. With the biceps, this is for flexing at the humeral nerve. The hamstrings are for flexing at the.
Oh, then that makes more sense.
Yeah. Okay, how do we name all these different muscles? I've been mentioning a bunch of different muscle names. They're named for a few different reasons. One, they could be named after the region that they're found. So that's pretty straightforward. There's a muscle called the brachialis that's found in the brachial region. It acts like the biceps brachii, which is why I want you to say the full name, biceps brachii. It's found in the brachial region. Or tibialis anterior, maybe you've never heard of this muscle, but you can take a wild guess where you can find this. Tibia, yeah, just anterior to the tibia. Here's the sharp part of the shin, just lateral of it. It's right here. It's where you get shin splints, if you've ever had those. Tibialis anterior. So you can name it based on the region. You can name it based on shape. Trapezius is kind of trapezoid shaped. So here's to the left trapezius, the other one would be right here. It's more like a kite to me, but yeah. Trapezius, trapezoid shaped. Or the deltoid, delta in Greek is this shape. It's a triangle. So the deltoid, triangular shape. So it could be named after its literal appearance. Like what does it look like? So body regions, shape. Could be named based on its orientation of fibers. The term rectus, you're going to see this come up a lot. Rectus means straight. Rectus means straight. So it's actually a pennant muscle, but altogether it's straight down the leg. Rectus femoris. So it's in the femoral region and it appears straight. Rectus femoris. Oops, sorry. Or external oblique. External means towards the outside, more superficial. Oblique means off to the side. That's your one of your oblique abdominal muscles. This root, CEP, C-E-P, that means head. CEP or cap means head. So biceps means two heads. So biceps brachii means two heads in the brachial region. It has two origins. There's two pieces to the biceps. The word teres means round. This is going to come up a lot. Teres means round. Major means bigger. So it's the big round muscle. Teres major. Where is the teres major? It's just inferior to your scapula, like right along the inferior portion of your scapula. We'll go over it, of course. It could be named after where it attaches. Here's a fun one. This is the sternocleidomastoid. Sternocleidomastoid. It has three attachments, as the name implies. Sterno, where does it attach? Attaches to the sternum. Cleido is clavicle. So it attaches to the sternum, to the clavicle. Where's the mastoid process? Posterior to the ear. Remember this? Sternocleidomastoid. It's this muscle that goes along your neck. Moving your neck. Here's one muscle, here's another muscle. It has like branches.
Is it different names?
Right sternocleidomastoid, left sternum. Yeah. We're not going to go over this muscle, but here's another one, the genioglossus. The term gloss, first for the tongue. So it could be named after where its attachment points. Could be named after its primary function. Flexor, and here's a mix of function and region. Flexor carpi radialis. It's a muscle that causes flexion at which region? Where's the carpal region? The wrist. It flexes at the wrist. It's on the radial side. Which one's the radial side? Lateral. So it's this muscle right here on the radial side of the wrist. Causes flexion. Flexor carpi radialis. Adductor longus. What does adduction mean? Bring together. So it's either going to be in the shoulder region or it's going to be in the thigh region. It's in the leg. It's a long muscle in the medial thigh that brings your legs closer. Adductor longus. Adductor longus. Sometimes they have crazier names like the buccinator or sartorius. Remember buckle? Buckle means cheek. A buccinator, that means trumpet player. When you're playing a trumpet, you're blowing really hard. You're using these muscles for blowing air to play a trumpet. Buccinator. Or sartorius. Sartor means tailor. If you're a tailor, like traditional tailors who cross their legs and sew or hammer or whatever. Or you can think about like if you measure your inseam. It's this really long muscle that starts from this anterior superior iliac spine and goes down to your tibia. Helps you cross your legs. So, I think there are like 7 reasons why muscles are named what they are. 7 different potential reasons why muscles might be named what they are. Just like we got a lot of practice with all the names of bones and their functions and locations, you're going to get a lot of practice with the muscles and their names and locations and functions. Any guesses what we're going to do in lab? Well, after the practical. Well, I mean, how? Like, how are we going to? I mean, we won't do. No, you'll see. You'll see. Okay. I'm sure you're all anxious to get ready for your practical. So, yeah, I'll see you in lab. Give us like, for those of you Monday, Wednesday, give us till like 11:20. Come by 11:20. We should hopefully be ready by then. Thanks. Yeah. How many muscles are there? I don't know off the top of my head. And we're not going to go over all of them.